1, 2, 3. Let's see if the audio works. One, two, three. Let's see if the audio works. Awesome. Okay, we can start now. Make sure correctly. Awesome. Okay, hello everyone. So this is my first live reading experience like that. I will be reading this paper, DiffRF, Rendering Guided 3D Radiance Field Diffusion. And we will be looking at this paper, trying to understand it step by step, starting from this website and going directly through all the paper. So I didn't pre-read this paper. I will be trying to understand everything, and you can see how I go about it and what's the process like. So you might be at some points struggling with me through it. But if this is interesting or you have any questions, you can ask any questions on chat. And yeah, let's dive in. So this is not necessarily the newest paper in the world, but it's definitely interesting. I think it was published on CVPR in June. And basically this paper looks at how we can apply 3D diffusion, how we can apply the concept of diffusion that is very popular in 2D image generation to 3D objects. Specifically, how we can create a radiance field with diffusion. So very typical thing, very often used is something called NeRF, which is neural radiance field, which is basically an implicit function that allows us to render objects from this optimized, basically small neural network. And here we will have this model that allows us to generate such implicit function and then retrieve object from it using diffusion. Interestingly, not only they use diffusion, but they also use volumetric rendering loss, which is very typical loss that you use when you train nerves. So what this model actually does, this model is actually like retrieving a nerve and trying to also optimize this nerve that is being retrieved from the prior distribution of 3D nerves using these images, this basically the views of the object. So it's kind of a combination of diffusion and neural radiance fields. And what I already see as interesting here is that they have these time embeddings here. I'm not sure if these time embeddings are specifically about diffusion, because diffusion have time embedding built in, where you do the diffusion. Each step of the diffusion has specific time embedding. So if that's the case, then it's very regular diffusion. But I think it might be that these time embeddings are more of a time embeddings that we see when we process videos. So basically step by step, frame by frame generation time embeddings. And we will later see if this is the case or not. Because if it is the case that there is these time embeddings that are typically used in video generation, then that means they probably stole some ideas from some video diffusion model and basically try to apply it to 3D. So the model is optimized using this loss that is, as I mentioned before, is a sum of this rendering loss, which is how different this object is after diffusion compared to the images previously taken, and this diffusion loss that is typical for any diffusion process. Okay, so they say using this two-term loss enables strong radiance priors with high rendering quality and accurate geometry. So we will see about that. How does it really look like? Let's look through the pictures here. Okay, so this is how this denoising is visualized step by step from some random Gaussian 3D noise into this radiance field that can be then rendered into this 3D object. So this is like assets from like a typical Photoshape dataset, often used like as a toy dataset for 3D examples. So this is like a chair class. We have tables from some other dataset. I mean, this looks okay. Obviously, the resolution is small. We will see what the limits on resolutions are imposed by the method they use and how compute intensive it is. And then we can decide for ourselves if we could potentially upscale that. Yeah, that's something interesting. But another thing that they are proposing here is this 3D mask completion. So the idea is basically, as you have in image, you can just like mask out some area and generate different fill for that area. This is very natural thing in Photoshop, for example, right now with Firefly. People are testing that a lot. So they have similar idea here. You create this volumetric mask and then you can receive the completion of the object denoised specifically in that mask. We will see how they implemented that. This is actually, I think, very interesting. Yeah. So this example, for example, looks very cool. I think like, we can get very different assets from this one asset here. So I think this is interesting for different variation and controllability for the user. So I like that a lot. Yeah. Here is image to volume synthesis. So this is obviously a very cool task, very important task for asset generation when you can just take an image and generate a 3D asset. Here specifically they say a post image. So you will have to have some kind of external information on the viewing angle and position compared to the object. And it's saying relative to the 3D bounded box. So we will learn about that in the paper, and we will think how that could be done in practice. So they segment the image, and basically they use diffusion guidance to basically minimize the loss not only between the in the diffusion process, but also the loss in terms of similarity between the rendering of the object and the actual image here. I mean, I think this is sensible for this. Obviously, the quality is not perfect, but I think we already saw the quality is not that big, not that great. So we will look at it and see how the architecture looks like, and we will see what's the output resolution for that. I think this example is much more successful, but also this example is much easier, where most of the object that is relevant is very visible, and this bottom part is not, and we see that there is different variation in the how the foot of the chair looks like. So it looks reasonable, right? But it's also the chairs, so they train probably on chairs and they can do more chairs. So I don't think this model will generalize well outside of these toy examples of chairs and tables. We will see if they tried any generalization or they don't even try that. Yeah, obviously you would like to use that for generating assets. Yeah. but this is, I don't think they tried that. So we will see. We will see how does that look like. Yeah. Okay. They also provide these links here. I think this might be work of their lab or something like that. Obviously, there is a link to Diffusion, which is, I think, the first example of diffusion for nerves. But this was 2D guided diffusion, so using 2D diffusion to generate nerves. There is this other example of Lion. I didn't read that paper, but there is some kind of hierarchical approach for cloud synthesis. And these video diffusion models, I looked through this paper. I think it's still very early paper for video diffusion. I think we have better techniques now because this is from 2022, and in the March of this year there were multiple cool videos like Anime Diff, I think, which is a great example of video diffusion that I think provides much better movement, camera stability, consistency, and better quality. So I would check out this if you're interested in video diffusion. Yeah. So I think that's it. So let's dive into the paper, and we can see what exactly is going on here. Yeah. So let's read the abstract first, maybe. The picture, I think, is reasonable. So we have volumetric diffusion. So we will see how that exactly is encoded. So this is typical diffusion process. We start from some time t, probably like 1,000 step or something, and then we move from Gaussian noise directly to the t times 0, which is like a fully generated asset. So we'll see how that looks like. Yeah, so that makes perfect sense. We will see how the mask completion work, because I don't know how they implemented that. So maybe let's read the figure 1 here. We are doing probabilistic diffusion process applied to 3D radiance fields, guided by 3D supervision with and volumetric rendering. Okay, so this is the concept of you render the object, you take a picture of the object from a specific angle, and you have other picture that you had in your training set, and you compare these two pictures and you calculate MSE loss, and this allows you to make sure that the objects look the same way from the specific angle as in the as required by the training set. So this is the volumetric rendering loss. Okay, so what's next? Model enables the unconditional synthesis of high fidelity 3D assets. Okay, yes, you can do unconditional synthesis. So that means basically what unconditional synthesis means is that you can just plug in random Gaussian noise and you get a 3D asset of some kind. In this case, sofa or like a chair asset. Okay, they do this mask completion. And they are doing it as conditional inference without task-specific training. Okay, let's take it closer for you guys to have easier time reading this. So that's cool because there is no additional training. So they figure out how to do this mask completion without a specific subtask. They don't do that as like a setting, like creating specific data sets with these masks. I think they just use the previous model that they trained on the full diffusion to do this task. So we will see how does that work, how this works. And I assume they basically use this input here as some conditioning information. That's probably what conditional inference means here. And we will exactly see how they did that. Okay. Cool. Okay, let's see the abstract. Yeah, so diffusion right now mostly works on images, or we have something called latent diffusion, but basically the idea is similar to regular image diffusion. So let's pull up some kind of picture. yeah, that's that makes sense. Oh, this is, I think, a good picture. Yeah. So basically, the point is you are introducing some kind of picture that is in the training set, and then you use some kind of noising procedure to make it more blurry until you get Gaussian noise. And you train model to just transform this Gaussian noise into less noisy version of that, less noisy version, and basically you train a reverse process of this diffusion to get back to this object. So we try to do that for images, and it works well. All of the text to image models right now are mostly based on diffusion. So yeah, I think this is fairly clear for anyone interested in diffusion, and there are a lot of material on that. Yeah, but basically what we do, we have this training set of nerves, so they will have to have some kind of 3D objects to generate these nerves, and then you noise them, and then denoise them back, and this is done for images very often. This is done for latent encoding of images. That means like already encode image, because we learned that basically doing this, the same process but in the latent space instead of image space, works much better. And they also mentioned that this can be used as for point cloud data. I think that's reasonable, but I personally didn't specifically saw any implementation of diffusion for point cloud data, but it makes sense. And they say they are first to directly generate volumetric radiance fields. Okay, so that's not very far from point cloud data, but let's see what exactly they do. 3D denoising model. They use explicit voxel grid representation. So when you hear voxel grid representation, you basically think Minecraft. So you have some kind of Minecraft, but on very small resolution of boxes, and you, for every voxel, for every box, you basically set some values that allow you later to render the image. So they have some explicit voxel grid representation, so we'll see how they use that. That's probably why they say radiance field rather than neural radiance fields, because that probably implies more of a nerve than voxel grid. Yeah, we will see that. Yeah, and basically they say, okay, so if we just generate these radiant fields, it's bad. They have artifact, and also getting these radiance fields is non-trivial, because what is radiance fields is basically this some kind of implicit function that represents a 3D object, and how you get them. So basically, to get these radiance fields, most often you take photos of the object from multiple angles, and then you can see basically that you can align these photos such that you get these radiance fields values for any point that you want to render. And that is by itself an optimization. So it's already noisy to some degree. And getting this ground truth data is difficult because you literally need to do a lot of photogrammetry and taking pictures of the objects. So that's what they mention here. We will see if they address that. Okay, we address this challenge by pairing the denoising formulation with rendering loss. Okay, so this is the concept of using specific photos of the object to get additional loss here, right? So one is this denoising loss here that is between this difference, and then you have this picture loss. Okay, so they use that. That's cool. And this, they say, this gives them better prior for good image quality instead of trying to replicate fitting errors like floating artifacts. So this is the problem of these radiance fields. When you create radiant fields, you might get some floating artifacts, right? But basically what they say, not only we generate these radiant fields as a ground truth, but also we have pictures from specific angles, and we know the angle, right? So then when we render the object, we can not only make sure that the asset aligns, but also we have a loss that controls so that actual picture of the object, not the optimized 3D nerf, but rather actual picture is the same as the rendered picture. So this way they can kind of ignore the artifacts that naturally came even just from using these ground truth radiance fields, right? Because just using these ground truth radiance fields is already adding some noise, and their system is probably adding more noise. So if they don't do this volumetric rendering, there is a lot of artifacts, and it's basically really bad. Okay, so they say that in contrast to 2D diffusion model, our model learns multi-view consistent priors. So this is basically the biggest issue with doing this 3D diffusion or like 3D generation in general, is that people already figure out very well how to take a one view and perhaps generate another view and from other angle of the same object, and these two views align quite well. But if you have to generate an object that is consistent with so many different views, then there is always the problem. So they say they solved that. I doubt it, but probably they made some improvements toward that. So that's great. And what they say else? Yeah, accurate shape generation, blah blah, marketing. Okay, so they compared to 3D GANs. Okay. This approach enables conditional generation, and they say this mass completion or a single view 3D synthesis as an inference time is possible. So that's great. Yeah. So generative adversarial network, probably most people knows the concept. So the concept of the GAN, let's look at some graphic that makes some sense. Is there some graphic that makes a lot of sense here for GANs? Okay. Okay, let's just use that, but I would rather have something with examples. But basically, GANs, you have some real images dataset. Open. Wait, this is. Okay, so you have this real data sets here, right? And you have some generator, and you have discriminator model. So this is adversarial because generator is competing with the discriminator. Generator is generating some picture, and the discriminator role is to decide, is this a fake picture or is this picture from real dataset? And you basically feed to this discriminator randomly, you add some generated pictures and add some real pictures from your dataset. Discriminator quickly learns to distinguish between fake and real pictures. So then generator can update its weights such that it generates better fake pictures. So the fake pictures here and the distribution of the data here aligns more with the real distribution here. And this way you basically create generation. So this is like a previous iteration of how most generative AI was done prior to diffusion. And one version of that is doing 2D GANs, which is most typical, which is basically generation of 2D images. But there were versions of doing this in 3D. So they compared to 3D GANs. That's cool, but I think it would be awesome if they could compare to also some other 3D methods that involve diffusion, because there were multiple of them. And 3D GANs are a bit old right now already, but we'll see what they say here. Okay, so introduction. They talk about nerves. Awesome. If you are interested about nerves, I have a video on nerves, so you can check it out. But nerves basically allow us to render these pictures with neural network. So we can optimize this nerve to generate these 3D objects. That's cool. Yeah, so nerves are powerful representation for generating 3D scenes from 2D input images. Awesome. Okay. And it has potential in AR, VR gaming, and other applications. Awesome. Okay, so they talk about different other works, showing how to incorporate sense semantics. That's interesting, probably. Training models from heterogeneous data sources, scaling them up to represent large-scale scenes. These advances are testament to the versatility of ML-based scene representations. Okay, that's awesome, we agree. However, they still fit to specific individual scenes rather than generalizing beyond their input training data. Okay, so quick note about this here. So basically what NERF does, you have these different pictures, you have this neural network, and for every object or scene, you need to train this small neural network that is the NERF. It's not like most neural networks, most deep learning, where you aim to train some model on some big data set, and then you aim to generalize and use that data set in different applications and use that model in different applications. For NERF, you need to have one specific training for one scene. So that's what they mean here. Okay. So they talk that neural field representations that generalize to multiple object categories or learn priors for scene across datasets appear much more limited. Yes, so that doesn't work well yet. So this is the idea. We would like to have one model to have different scenes and encode different scenes. One training and then generalize. That's what we would like to have. This doesn't work well yet. Yeah. Despite enabling applications like single image 3D object generation and unconstrained scene exploration. So this is like typical applications we would love to have, but it doesn't work. Yeah, these methods explore ways to disentangle object priors into shape and appearance-based components, or to decompose radiance fields into several small and locally conditioned radiance fields to improve scene generation quality. So these are some ideas here. So yeah, have different nerves to generate different parts of the scene, have different objects to generate shapes, and different objects and different nerves to basically generate textures, but it still doesn't work. Yeah, so we used GANs, awesome. We used GANs in 3D also, and there are some good results with that. But the training of GANs is really terrible experience. We know that from 2D GANs, I just showed you previously. You need to these two competing neural networks, and it's very easy to find yourself in some local minima and for the training to collapse. So we hate training GANs basically, and that's why diffusion models are much better, especially at scale. Yeah. But they also talk about this, that basically even if you train these 3D GANs here, most methods, I would say, still generate the 3D asset, then render some specific view of the 3D asset and compare to the image. They do not compare the 3D asset itself. So that might be also a problem with this method. And they discuss diffusion-based models. So this is what we use for generation now. So let's see what they talk about this here. Yeah, they perform or par or surpassing GANs. I would say they beat GAN in every task, and they are much better in every dimension you can have. So yeah, diffusion-based methods, awesome. Yeah. producing photorealistic images, almost indistinguishable from real photographs, or sometimes completely indistinguishable. And for multimodal or conditional settings such as text-to-image synthesis, we currently observe unprecedented output quality and diversity from diffusion-based approaches, right? So this is all of your Midjourney, DALL-E, Stable Diffusion, etc. models. Obviously, it works very well. While several works address purely geometric representations, lifting the denoising diffusion for simulation directly to 3D volumetric resonance fields remains challenging. Okay, let's think about this. So, address purely geometric representations. What do they link? 35. Diffusion pricing models for 3D point cloud generation, okay, and 78. 3D shape generation and completion through point voxel diffusion. Okay, so basically what they mean, these are the works that do very similar thing in my probably, but they use like voxel explicitly. But it's interesting because, or point clouds explicitly, but they also say they use voxel explicitly. So we'll see what's exactly they mean. What's the difference between their method and fundamental difference between their method and these methods. And these methods are lifting the denoising diffusion formulation directly to 3D volumetric radiance fields and remains challenging. Okay. So basically, probably these methods have some additional bells and whistles that makes them not necessarily fully a diffusion solution. So they say, okay, now we're gonna do actual diffusion. That's probably their argument here. We will see. I don't know these other works, so that's probably something that could be arguable, but okay, that's their point. Let's look further. The main reason lies in the nature of diffusion models, which require a one-to-one mapping between the noise vector and corresponding ground truth data samples. In the context of radiance fields, such volumetric ground truth data is practically infeasible to obtain, since even running a costly per sample nerve optimization results in incomplete and imperfect radiance field reconstructions. So this is what we mentioned in the abstract, right? So to train the diffusion model, you need to first get some ground truth data, some, for example, image samples if you do image diffusion, and then you noise the image with some Gaussian noise. So that's, you can always do, add Gaussian noise to the picture, but you need to have this clear image to then be able to train the model. And here your clear image is this nerve, right? And the nerve itself, right, has errors, because nerve itself is some kind of deep learning process where you use different images to, per sample, optimize this small neural network so that you can get these radiance fields, right? So they talk it's infeasible because it's costly, because you need to do this nerve for every object that you want to render, and that's all true. And I think this is very clear that this approach of using nerve as a base of this 3D generation is probably completely bad approach. I think they're gonna still use the nerve, but they basically say, how about we use this nerve, but or some other 3D model data, but we also use this rendering. But let's see. In this work, we present the first diffusion-based generative model that directly synthesizes 3D radiance fields, so aka voxel field nerve thingy, thus unlocking high-quality 3D asset generation. Yeah, high quality. For both shape and appearance, our goal is to learn such a generative model trained across objects where each sample is given by a set of proposed RGB images. Okay, so it seems they are actually not doing this diffusion in the standard way, because they say that each object is just given by the set of post RGB images. So they just use the images with the information how the camera is angled at the object to train. So they don't actually use the nerve to train. So that will be interesting. So this is basically more similar to nerve itself than just training using nerves, because that's how nerves generate these 3D assets, right? The nerves generate 3D assets by taking different images and trying to optimize a function such that every image, right, is correctly returned from the rendering for all of these images, and we minimize the loss, and we hope that if we pick some other angle that is not in the training set, we will still get great asset. And they basically do the same thing as you would do normally with the nerve, but they use it as a training procedure for this diffusion 3D models. So we will see how that works. And that's more interesting than just using nerves or 3D objects. So we will see. Obviously, to get these post RGB images, right? This is very different from just getting RGB images, because when it says post, it means that you will have to have the camera angle and the viewing direction, probably, or something like along this line. And that is often difficult to get in regular images. Like, images don't have that. So what people do often, they generate this from 3D assets. So I assume, and you will see that later, that probably they still use some synthetic 3D assets to train, but instead of training on the 3D asset itself, they first take the renderings of these 3D assets, and they train using just these renderings. So yeah, because if you have a 3D asset, right, you can put your camera however you want, and you exactly generate the view of the asset, and you can save the specific viewing direction and the camera position, right? So then you get this post part, which is the biggest issue. Okay. So again, they say they operate on explicit grid representation. Yeah. To address the ambiguous and imperfect radiance fields representation for each training sample, we propose to bias the noise prediction formulation from the noise in diffusion probabilistic models, which is the most important paper probably on diffusion that introduced the diffusion models. That's typical reference here. And they want to bias it towards synthesizing higher image quality by an additional volumetric rendering loss. So this is for, I think we mentioned this volumetric rendering loss for like 7th time. Yeah. This enables our method to learn radiance fields priors less prone to fitting artifacts. So this is remove artifacts idea, or noise accumulation during the sampling process. We show that our formulation leads to diverse and geometrically accurate radiance field synthesis producing efficient blah blah marketing. View consistent renderings, we will see about that, because that's the biggest challenge always, which is if you change the viewing direction from not something that was in the training set, but maybe some completely different viewing direction, can you actually see two pictures of the same object, and in your mind, do you think this is the same object, or is there something weird and it looks like two similar but different objects? So that's the biggest issue, if this is actually view consistent or not. Yeah, our learned diffusion prior can be applied in an unconditional setting where 3D object synthesis is obtained in a multi-view consistent way, generating high accurate 3D shapes, blah blah, free view synthesis, blah blah. Okay, we'll see about that. We further introduced the new task of conditional mask completion. We saw that. In this setting, we allow for realistic 3D completion of partially masked objects without the need for task-specific model adaptation and training, which is cool, I think. To the best of our knowledge, we introduced the first diffusion model to operate directly on 3D radiance fields, but actually on voxel grid representation specifically. Enabling high quality truthful 3D geometry, and okay, we'll see about that. And we introduced the novel application of 3D radiance field mask completion. That's cool, which can be interpreted as a natural extension of image inpainting to the volumetric domain, which is also something we mentioned, I think, which is like, this is similar to how we inpaint images. we show compelling results in unconditional and conditional settings by improving over GAN-based approaches and on image quality. But this FID is still very high. So FID is a metric for looking on the quality of images. I think it's not the best metric in the world because it's just using some encoding from a specific neural network to compare how good the results are. But we would hope for FID of like 6 or 5, and we have like FID of 15. So yeah, not the best situation. And they use challenging Photoshop chairs datasets. So I don't think this is very challenging datasets, but sure. So now we will go into diffusion models related work section. And again, this is like very typical introduction to diffusion model. Every paper has that. So we will look through this very quickly. Diffusion process, denoising score matching. Denoising diffusion probabilistic models is the big one. Single framework coin score SDE. This is how we also can call the diffusion models basically. Blah blah blah. There are different work exploring different formulations, training algorithms, samplings, etc. A lot of stuff is going on with the diffusion models. We know that. State of the art in text to image and guidance synthesis. And they say 3D shape generation. Let's see what they quote here. 6, 35, 77, 78. So 6 is what? Okay, I don't know this paper, but it's pretty old. It's 2020. 78 is 3D shape generation. 77 is latent point diffusion models for 3D shape generation. That will be probably more interesting one. Okay, cool. Yeah. Video generation also. Okay. They outperform GANs. This is very interesting. We know that. Much easier to train. This is the crucial part, which is it's actually quite reasonable when it comes to training time, and also when it comes to the fact that basically it's much more much easier to predict that it's gonna work. For GANs, there were so many issues with training collapse that it was very hard to say the training will work or not in the end. So very cool that diffusion actually works very well, and we can use that. But the training is still relatively long, but I think training now with the current state of scaling the models and compute, it's always gonna be increasing. So it's cool that it's actually working. So, yeah, let's go further. 3D generation. We used GANs to generate meshes, to generate 3D textures, to generate Minecraft-like voxelized representations, and most importantly, nerfs. Yeah, a lot of attention put to nerf. Blah blah blah. PyGAN was like a very popular GAN solution that worked quite well for a GAN. Yeah, so they basically discussed that these models kind of do similar thing that they're gonna do, but use GAN instead of using diffusion. So standard nerve model is cast in a GAN setting by adding a form of stochastic conditioning trained with an adversarial loss. These approaches are partially limited by the high training time memory cost of nerves type volumetric rendering, right? Because nerves are costly, forcing them to use low resolution image patches. Cool, but looking at your resolution, probably you also use low resolution, so okay. So some solutions solve this issue by letting the volume rendering component output a low resolution 2D feature map, which is then upsampled by an efficient convolutional network to produce the final image. Okay, this approach drastically improves the quality of resolution of rendered images, but also introduces 3D inconsistencies, as the convolutional stage can process different views of the same object in arbitrary different ways. So this is again the issue. If you want to get a high quality output that is consistent, multi-view consistent, it doesn't work, because whenever you put additional layers on top of anything that you train specifically for this 3D consistency, it will generate a bit different results in the end, and you lose all the consistency, right? Steiner, they basically do these convolutions better, and EG3D, they use this three-plane representation, which kind of works a bit better than NERF because it produces less artifacts, but I think this is still in a way focus on GANs specifically. So this, in contrast to this, GAN-based approaches do not naturally support conditional synthesis or completion, right? So actually this EG3D, I think the team where there is a researcher from my university actually work on the extension of this EG3D to allow for this conditional synthesis or completion, but this is still basically using some kind of diffusion there. But in the end, they use these three planes and they use GANs, so it's still GAN. Okay. Compared to GANs, diffusion is underexplored. 3D point clouds can work with the diffusion, showing promising results. There was the Diffusion paper, very popular, that actually started off this direction into 3D. At least there were much more work with this Diffusion. And they also use these Radiance fields with conditional text and images and unconditional 3D generation. Okay, so Diffusion, I think we can show that really quick. So Diffusion was, I think, very cool research because it showed the ability of using 2D diffusion models, like for example stable diffusion, to generate 3D images by basically generating 2D images of the object from different angles and training a NERF on top of that. Obviously the quality is not the perfect one, and this could be improved in many different ways. There are many issues. These are still like very cherry-picked examples, so if you do something else, probably it's not gonna work that well. But this opened up this direction of research. That was very cool. So they talk about it here. So they say this presents an algorithm to generate NERFs augmented with an illumination component by optimizing a loss defined by a pre-trained 2D text conditional diffusion model. So yeah, they use the pre-trained to the 2D text conditional diffusion model, so basically like a stable diffusion. Yeah. And this solution does something a bit different. They first train a conditional NERF to reconstruct a set of indoor videos given scene-specific latents, and then fitting diffusion model to capture the learned latent space. So it feels this probably is similar, but it also have like a per scene optimization process, which is not the best. And some other works that are currently being developed the same time as this paper was developed, they try to apply denoising diffusion to factorize radiance representations. In contrast, our diffusion model operates directly in the space of radiance fields, which directly enables 3D conditional tasks like shape correlation by leveraging the learned volumetric prior. So basically they say instead of doing any 2D diffusion, we're gonna do directly 3D diffusion, and this allows for this masked completion. So that's awesome. We like that. Okay, now we will finally go into the meat of the whole thing, which is their method and what they are actually doing. So let's see. Okay, so their method consists of generative model for 3D objects that builds on recent state-of-the-art diffusion probabilistic models. Okay, it is trained to revert a process that gradually corrupts 3D objects by injecting noise at different scales. Okay, we understand diffusion now. In our case, 3D objects are represented as radiance fields. So the learned denoising process allows our method to generate object radiance fields from noise. So interestingly, here again, it seems more like the ground truth will be these radiance fields, because they say we're gonna take the radiance fields, we're gonna corrupt it, and we're gonna denoise it into the ground truth radiance field. And this will allow us to do that from noise by just initiating some random noise in 3D. But previously they mentioned they're gonna just use images instead of post images. So let's see what actually they do. And because now I'm a bit confused, I mean, they say one thing in one place, other thing in the other place. Let's see. Since we target generation of 3D object as radiance fields, we begin with brief overview of this representation before delving into the details of our method. Okay, so now guys, again, we're gonna have kind of nerves again. So if you watch a video on nerf, that will be a revision for you, but let's see exactly how they represent this nerf here in this paper. Okay. Okay, so radiance field, which is represented by sigma eta like that, is an implicit volumetric representation. Implicit meaning it's an implicit function. It's a volumetric representation because it's 3D. So it has volume of a 3D object that is given in terms of density field. So sigma is the density field, which is basically saying how much content, how much matter is in particular space in 3D, and an RGB color field, which is basically returning what kind of color this point in the field has, right? So specific point can have high sigma, that means there is a lot of object there and we should render some color there, or low sigma, there is basically an error here and we should not render anything here. And there is also this color, so for every place, even if the sigma is small, we will still get a color, but if the sigma is very small, we will just ignore this color, and if the sigma is high, we will use that color to render a pixel in the image. So that's how we use these implicit representations in nerves. So this should be actually green. We will use green for any notation in the paper. Yeah, and it's defined over 3D domain. That's okay. And then density field gives us information about the presence of an object in a specific point in space. That's what I said. Whereas the color field provides the eventual corresponding RGB color, which is exactly what I said. Following a ray casting logic. So basically when you render this stuff, you have a picture and you put a ray through the scene in some specific direction, and you calculate sample different points on the trajectory of your ray, of your light ray, and you check, okay, what is the sigma value, what is the RGB color value, and you sum up all of these colors to get your pixel value for the image. So basically this is what it's saying here. So so there is some kind of viewing direction error. So this is your ray. Error is the R is the ray viewing direction, and there is RGB color that is being found, and for the particular ray, and the ray is going to output basically a value of the specific pixel in your actual rendering. So when you render stuff, you pick a position and you render the picture, right? Which is in 2D. So for every pixel you have a ray, and this ray basically is gonna output the color of the pixel in this RGB image. So this is the output, right? And we just calculate this as a summation over this this ds, which is your sampling step, and yeah, we will just look at that in a second. So R is the linear curve parameterized by S with unit velocity rs. Okay, so S is unit velocity, so it's some kind of the same jump over this line, so probably some kind of 1, whatever the 1 means in this 3D coordinate system. And rs denotes the point along the ray at S. So this is all the different points that you can sample the values through this particular line. And tau S of R is the transmittance probability at S, which is given by basically this sigma-like thingy, which is basically this term is saying how much content is at particular position on this whole array, right? And this is exponentiation, and this is the calculation of the sigma over all these steps, right? Over all these steps on the array, how much content we should display. Yeah. Using the ray rendering equation above, we can render the radiance field from any given camera, yielding an image of a novel view. Okay, and it is sufficient to turn the camera into a proper set of rays expressed in word coordinates. Yeah. So basically, when we figure out what kind of rendering we want, we set up this camera and we can just shoot the rays into the 3D space and calculate all of this information thanks to this tau of S, sigma, and eta, I think this is like large eta better. Is it large eta? No, wait. This is a large sigma. It might be a large sigma like that. Okay. Yeah. So over this, basically these colors and this sigma, and this is also dependent on sigma. So basically, all of this is represented by this radiance field nerf, because we can always get sigma for any point due to this nerf, and we can get always the RGB color due to this nerf. So whenever we need a point, we just sample the point we want to get values for, we put it into this radiance field, and we get back all of this value that we need to calculate the CR, and CR is basically the color of the picture of the image, so that's how we render the images, and that's again how nerfs work. Yeah, this is a quick revision on nerf. They say that there is various of ways of implementing a radiance field, ranging from neural networks, which is nerf exactly, to explicit voxel grids, which is same concept, but instead of doing fully implicit representation, you divide the 3D space into boxes, and then you have these numbers for every box instead of having a neural network that returns it in continuous space. And in this work, we opt for latter, since it enables good rendering quality along with faster training and inference, because you don't have additional neural network. The explicit grid can be queried at continuous positions via bilinear interpolation of the voxel vertices. So they basically interpolate between the values on two different voxels. So if you want to pick some kind of point that is in between two voxels, they just pick a value between these two, the closest values in 3D space. Yeah, under the explicit representation, radiance fields becomes a 4D tensor where the first three dimensions index a grid spanning X. So first three dimensions are basically the position in the 3D space, and the last dimension indexes the density and color channels. So the last, so basically the first three is the position in X, Y, Z, and the last is these values here, right? So this is how you do the voxel grid representation. Awesome. So now we know how we're gonna render this stuff. So how they now gonna generate these radiance fields? Let's look into that. Okay. Yeah, so they do diffusion probabilistic model, awesome generation process, denoising process is governed by discrete time Markov chain, okay, defined on the space of all possible pre-activated radiance fields expressed as flattened 4D tensor of fixed size. So they flatten this 4D tensor to a fixed size, okay. We consider pre-activated radiance fields where both density and RGB color channels span a linear space, and we assume a proper activation function will be applied at the time of rendering. This is required to have additive noise while preserving a valid radiance field representation. Okay, let's think about it for a second because that sounds complicated. Okay. So basically, what they say here, they don't bound the values of this. So basically, obviously, there is natural boundaries for all of this, right? So sigma is not necessarily bound, but RGB colors are from 0 to 255 for every color, and then RGB and then sorry, XYZ coordinates are also bound, right? So what they say, we don't bound them, but we just assume that when we render, we have some kind of activation function which is basically gonna clip the values to the or clip or do some softmax, we will see exactly, to make sure that the values fit in these predefined boundaries, right? And this is needed because they want to have additive noise, which basically means they want to add Gaussian noise to these numbers, and if you have some additional constraints, like for example the color cannot be bigger than 255, then if you add some Gaussian noise to the color 255, then you could end up with color 300, and that's not gonna work, right? So they just use, okay, we assume it can be any values, and then we're gonna render it with some specific activation function, so it still should work. So that's clear. Okay. And then they have this Markov chain, so that's how the diffusion works. So these are all these steps when we noise and then denoise the object. Okay. Blah, 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 blah. So this is standard diffusion description. Yeah, so that's basically what they say here is that they are training this P theta, and this P theta is basically, this is our model. The model is gonna take the state of this flattened 4D tensor of fixed size on the some time t, and using that, it's gonna predict the object on the time t minus 1, which is basically from the more noisy one, get one step less noisy, right? That's what the model is gonna be trained to do. And we're gonna train this model with parameters theta, right? So we have this process here, which is like a standard diffusion process where we have this, that this is basically generated from the Gaussian noise, where this additional noise added is based on the time t and the feature vector on the previous state, okay? And this happens until we get f of 0, which is fully denoised object. Awesome. So we will use this reparametrization trick that everyone uses, which basically allows for more stable learning, but it's the same thing. And it doesn't need, because if we do that here, right, we would need to noise steps by step. If we do that, we basically can calculate what kind of noise would there be if we would take X steps, for example, 5 steps, and this way we can calculate this noise here that has been used to corrupt some particular ft-1. And we have these predefined coefficients. Yeah, so let's see if they train the covariance, because some papers train covariance and some just set it to the constant. Covariance take a predefined value, although it could be data dependent, okay? Additional details about the value that the predefined variables take are given in section 3.3, okay? Maybe they talk about it later. And yeah, and this is like our standard diffusion process. So we use this alpha t and beta t to noise your image. Yeah, so we're not gonna focus on this diffusion per se because we already discussed it multiple times. Okay, let's look at the training objective because that's specific to this paper. So our training objective comprises of two complementary losses, LRF, that penalizes the generation of radiance fields that do not fit the data distribution. So that's typical diffusion, so how well you can denoise the data, and an RGB loss geared towards improving the quality of rendering from generated radiance fields. So that's the picture loss. Okay, we derived the training objective for our model starting from a variational upper bound on the negative log likelihood. Okay, this upper bound requires specifying a surrogate distribution that we refer to as Q. Okay, interesting. Because it indeed corresponds to the distribution Q governing the diffusion process, establishing the anticipated fundamental link with the generation process. Okay, let's read further because I have no idea what that means. We provide some here key steps of the derivation of the bound and refer to 24 for more details about the intermediate ones. Okay, what is this trick exactly doing? This is the standard diffusion equation here. What is 24? Ah, this is the standard diffusion. That's why they are writing about it here. I don't know. Okay. Yeah, this is the standard equation for calculating diffusion. Okay. Yeah, and this is how you get this result. So basically, yeah, you have a loss where using this your parameters theta, you want to have f. So f of 0, which is basically your fully rendered object, and you train it by eliminating the loss so that your predicted noise is the same as the noise generated by the standard Gaussian Gaussian noiser, right? This is very typical for the diffusion. Okay. What else? Radiant field rendering loss. Okay, so this is the loss from the picture. Okay. Indeed, the Euclidean metric on the representation that is implicitly used in the previous loss to access the quality of generated radiance field does not necessarily ensure the absence of artifacts once we try to render the radiance fields. Okay, so this is again same thing. Artifacts gonna be there if we don't have some additional way to allow for this multi-view consistency. And they define this loss as a sum of time-specific terms. Okay, similar to 8. Okay, so this is same as in the regular diffusion, interesting. Oh, so cool. So they not only use that loss when they do at the end of the diffusion process, they use it while they do diffusion process. So for every step, when they compare the noise, then they do the denoising with the unit, they actually also do this comparison of how the specific view look like for the object. Okay. So for given radiance field F, a viewpoint V, we denote by RV of F the image obtained after rendering F from viewpoint V using equation 1. So this is your typical, so this is RGB image that you got by choosing a camera view, and you have this radiance field, right, which is being diffused, and you generate some image, right? And we also denote by loss B, Fe, the Euclidean distance between the rendered images from viewpoint V using radiance fields F and ground truth image EV from viewpoint V. Yeah, so here basically, whenever you do the diffusion, for every diffusion step, you are denoising and figuring out what kind of noise was added to the image in the last step. But also, what you do, you just take the current state of the diffusion model, you render it. Obviously, it will be noisy because the latent is noisy, but you compare this rendered image with the actual image from that viewing direction, and you calculate loss this way. And with that, you aim to condition the process of denoising to make sure that the specific viewing photos that you have with the specific viewing direction works well. So yeah, that's very cool. The idea is to compare the rendering of a given radiance field F0 sampled from the data distribution corrupted with T diffusion steps, and then fully denoise against the original ground truth image EV used to obtain F0. In theory, this implies sampling first FT from Q FT F0, which is basically first you sample some kind of noisy image and then sampling back F0 from our model, right? So this is like pick your ground truth object, put it through the noise, so you have now noisy object at time t, and then use the model to retrieve the F0, which is done through this process. This is, however, computationally demanding, and we resort to a simpler approximation. Okay, so that's awesome because that would be very painful. From the definition of DiffRF, the loss pushes towards having. This is the main concept of diffusion, where we figure out how to have this noise calculated, from which we can derive the approximation F0. Okay. We can then define our rendering loss as, okay. So basically, instead of rendering this F0, they pretend they have F0 by taking F0 and adding to it the error that comes from this noise error, right? Because this is basically the difference that you want to minimize. So if it's perfect, this is equal 0, so you'll basically have a 0. But it's not perfect because you for sure have some difference here. And this is multiplied by the coefficients that are related to how further in the diffusion process you are. So if you are far in the diffusion process, this is considered much more than if you are close to the fully visible F0 item, right? So this basically approximates the solution so that we don't have to fully render the object, and we can just use this as output from the network that is calculating noise, right? So this makes the training much faster. Awesome. And this works as expected, and we have some weight here that basically regularizes how much do we care about this viewing loss and how much we will care about the regular diffusion loss. Okay. Where the expectation is taken with respect to a prior distribution for the viewing point V, and the noise is generated from the standard Gaussian distribution. Since the approximation is reasonable only with steps t close to 0, we introduce a weight Wt that decays as step values increase we use WT equals to squared AT. So basically they say, okay, this approximation is good only when we have close to like 1, 2, 3, 4, 5, 6, 7 and not 1000. So we also, if we are at the bigger value, we're gonna care about this loss less. And this makes also sense because when you are on the more noisy part of the object, right? You cannot really compare the full noise to the actual image. It's never gonna work. So you want to care more about it the more you get back to the fully view image. So that makes perfect sense. Yeah. They do some ablation study when they show if it's actually helpful or not. Awesome. And this is the final loss that they use. Awesome. Obviously they do UNet, but they have to do 3D UNet, which is interesting, which is based on the 2D UNet architecture introduced in old paper on diffusion by replacing 2D convolutions with and attention layers with corresponding 3D operators. So 3D convolution and 3D attention layers. For training, we sample between 1 and 1000 for all experiments with variance of the diffusion process, with variances of the diffusion process linearly increasing from B1 to BT. There are different ways to do this diffusion process. This basically decides how fast do you denoise and how fast do you go back to the full image. And they use this specifically linear process. Yeah, so different papers use different settings here and they have different results, but let's go with that, right? And choose to weight the rendering loss with this parameter that we already discussed. And we can check in the appendix for more details on the specific architecture. Awesome. So I think it's very clear what they do. Obviously, the 3D UNet architecture is interesting. We will look into that later. But I like the most from this method, I like the idea of this WT parameter that basically considers the fact that when you are more in the diffusion process further back where there is only noise, we don't really care about the image correspondence to the images because it's just noise, so we cannot really do that. And I like the fact that they figure out this way of approximating the f0, because if they don't have this approximating of f0, if you would need to render f0 actually fully and not just calculate the noise, the whole process would be very painful and training would be extremely more expensive. So very cool. Let me take a sip. So now we will see how they evaluate the methods. Okay. They use this Photoshape chairs dataset, Amazon Berkeley objects dataset for tables. We provided 15,000 chairs using Blender API from 200 views on an Armadial spiral. Okay. For ABO tables, they provided 91 renderings with 2 different environment map settings for per object, resulting in 1600 tables. Okay. Since both datasets do not provide Radiance feeds representation of 3D objects, we generate them using voxel-based approach at resolution of 32 to the third from the multi-view renderings. Yeah, so they need to, so as we see, for training, again, they actually use a 3D dataset of chairs and tables, and to get these post images and the post images will be used for specifically for this rendering loss, but they also need, so they not only use post images, they also need this voxel based representation. So they are actually gonna render for every object this voxel based representation, and they quoted this as very costly, very inefficient, blah blah. They obviously do the same thing because there is no better solution right now when people do this kind of research yet. yeah, they use different metrics that are typical for image generation and could be used also for 3D asset generation and 3D rendering generation. Um, And they use resolution of 128 times 128, which basically probably corresponds to the fact that doing it in a higher resolution probably is prohibitive because they don't have that much compute and their unit architecture is also very demanding. We'll see about that in a second. But obviously, doing 3D stuff is requires much more compute than like 3D attention, or doing 3D convolution requires much more than doing the same thing in 2D. So the resolution is bad. Okay, they do some comparison here. Cool, they compare all these methods that I mentioned before. They use the same images for training. Okay, they do some pre-processing to render images to create a radiance field representation for each of the shape samples. The GAN-based methods are trained directly on render images. Okay. Compared to these approaches, our method is overall better image quality while achieving significantly improvements in geometrical quality and diversity. Okay, we'll see figure 3. Okay, so that's the Python, that's the Edge 3D, which is doing this triplane stuff, and that's their method. I mean, obviously it's unconditional, so these objects are completely different, so it's hard to compare that directly. I think there are many more artifacts here, definitely. I think this Edge 3D is better than this one for sure, and might be comparable, I think. Yeah, but let's say this is better, okay? Let's agree with them for a moment. And figure 4 show a qualitative comparison of our method with Python and Edge 3D, okay? On tables, okay? So on tables, it seems it's better because there are these discontinuities. Yeah. So on tables, I like it more than E, and definitely more than this Python one. So it's probably better than these two GAN-based approaches, but I would like some comparison to these concurrent methods for diffusion, because that might they would probably much better than this Python and Edge 3D, but that's okay. While H3D achieves good image quality, it tends to produce inaccurate shapes and view-dependent image artifacts like adding or removing arm stairs or changing and supporting structure, as the training objective is to invert the diffusion process to denoise towards detailed volumetric representations. We observe that DiffRF reliably generates radiance fields with fine photogrammetric metric details, blah blah. Awesome. They say their method works. Cool. Contribution of rendering loss. Table 1. So these are the results, and we see that FID is 15, much better than the Python and similar to H3D. Key ID better. COV, what is the COV? The COV metric? Coverage score. Okay, coverage score measures the diversity of generated samples. Okay, I don't know this metric well, but it seems it's much better. And interestingly, without the 2D support is better for coverage, but that's probably because the metric is not just bad. It's probably just adding some additional artifacts, and that's because of that, metric thinks it's more accurate, or adding more stuff that is less consistent, multi-view consistent, and because of that, it's a new thing, so the coverage is increasing. I don't know, maybe. Okay. Okay. It's better than guns. Awesome. Additional to the rendering loss, improve image quality indicated by drop in quality without it. Okay, awesome. Cool. Contribution of rendering loss. Awesome. Removing to the supervision. noticeable effect of FID, etc. This shows that biasing the noise prediction formulation from the DPM by volumetric rendering loss leads to higher mesh quality. So adding this new volumetric loss makes this denoising better. Awesome. Very cool. Okay, now we go into this interesting stuff with these masks. Conditional generation. GANs need to be trained in order to be conditioned on a particular task, while diffusion models can be effectively conditioned at test time. Okay, we know that. We leverage this property for the novel task of mask radiance field completion. Mask radiance field completion. Okay, this is the cool stuff. This is done for in-painting, yes. Aiming to fill missing regions within a geometrical representation or in an image respectively. We propose to combine both in the novel task of mask radiance field completion, give a radiance field and 3D mask synthesize, and completion of the 3D mask region that harmonizes with the non-masked region inspired by repaint. So this is probably some, let's see, some 2D version of that. Repaint in painting using denoising diffusion probabilistic models, yes. Inspired by repaint. We perform conditional completion by gradually guiding the unconditional sampling process in the known region to the input F in. Okay, so F0 at time 10 minus 1 equals this. Okay. This is dot product, I think, here. Okay, and ft minus 1 is typically sampled, where m is the binary mask applied to the input, light blue, in figure 6, and denotes element-wise multiplication. Okay, element-wise multiplication on the voxel grid. Oh, that's why they decided to use voxel grid instead of nerf. Okay, that's now explains really why they decided to use voxel grid. So this allows them to do this masking much easier. So what they actually do, they have this mask M, and if the mask is present, they just take the if the mask is present, they just take the so if the particular point is unmasked, so it's preserved, they just take it, okay, and noise it. And if it's not unmasked, they just sample some predicted version of that. Okay, so that's how they basically distinguish between which region of the image should be denoised and which should be kept as it was. That's cool. So that's why they decided to use voxel grid. So that's very important idea here, is that this allows them to do it fairly clearly. Blah blah. We compare our method against Edge 3D at different levels of masking. At each level, we can only mask 200 samples and evaluate the completion. Blah blah. Okay, so they compare to Edge 3D. We use mask gun inversion where we perform global latent optimization to minimize the photometric error on the reprojected unmasked regions. We notice that due to signal latent code representation, Edge 3D struggles to faithfully reconstruct the unmasked region of the input sample, and regularization is needed to not corrupt the overall representation. Figure 5 further shows qualitative comparison performance against Edge 3D. Okay, let's see how it looks differently. 5, okay. Yeah, so that's bad, but that's not too bad. I mean, some of them are bad. This is clearly more consistent, but some of them are okay, I think. So, yeah. Could be better, could be worse. Let's see here. Mask radiance field completion for a train denied and given the mask region. Completion can be obtained by iteratively fusing the mask region with the estimated noise and applying the diffusion resulting FT. Yeah, so this is how they do this operation graphically. So let's look at it. So yeah, this is the input. So this is what we keep, and we want to have it working. So this is some random noise. We do this input mask. Okay. So to get this t-1 version of the input, we merge this part of the mask, which is the real one, and the one that is coming from the diffusion estimated at particular time. And we noise that, and we get more noisy version of the diffusion. So basically, at the beginning step, you have still ground truth. So this is perfect. This is perfect. And you keep this part, and you take the part that is masked, and you merge it together, and have the ground truth again, and then you add some noise, and then this part that is unmasked is predicted from this in the same way using this calculation here, and this is the same type of calculation that was done previously when they did the image guidance, right? So this was shown somewhere over here. Let's find the equation exactly. This was the trick that they used to not have to render this thingy multiple times. Yes, this is here. Yeah. Yeah, so because of that, basically this part, they don't have to render this f0 of t, they just estimate it with the noise difference and f0, that is the base picture. So they basically, for every step, when they need to noise again with this mask, they basically take the base one and they take the previous signal of the noise, and based on that they calculate exactly what should be this more noisy representation, where the top part is unchanged and the bottom part is being denoised. So that's very cool. Okay, so that's awesome. Very cool picture to explain that process. Cool. What else do we have? Okay, let's get back here. So they talk about that Edge 3D doesn't work always. We see that it fails sometimes, like here it's bad, right? Cool, let's look further. Okay, image to volume synthesis. DiffRF can be used to obtain 3D radiance fields from single view images by steering the sampling process using volumetric rendering. Okay, for this we adopt the classifier guidance formulation from 17, which is denoising diffusion models, probabilistic models, to guide the denoising process towards minimizing the rendering error against posed RGB image with corresponding object mask, obtained from, for example, with off-the-shelf segmentation networks. Figure 7 shows qualitative results for this single image reconstruction task on charts from ScannedNet. Furthermore, we show results of our model conditioned on clip embeddings, 48 in appendix, very interesting. Appendix, clip embeddings. Conditioning, okay. Yeah, so they also allow, I think, then for image conditioned with the clip. That's cool. Okay, and where is the picture for that? Figure 13, figure 14. Cool. So they also can use clip here. Very cool. More into that later. Okay, so that's the classifier guidance. That's standard thing. Okay, clip we can do. Okay, we can see in the appendix, blah blah. While our method shows promising results on the tasks of conditional and conditional ranges field synthesis, several limitations remain. Compared to GAN-based approaches, our Radiance fields-based approach requires sufficient number of post views in order to generate good training samples and suffers from lower sampling times. So basically, this is the issue. We again need a 3D dataset to do that because we need these post views to build the nerve voxel field representation, but also nerve representation or whatever radiance field representation you do. And you need the post images to do this additional conditioning that allows you to remove some of the artifacts. So basically it's limited to whatever 3D dataset we have, and we don't have much 3D datasets to do that. And it also obviously requires a lot of time to sample all of these views on the 3D objects. Okay. In this context, it would be interesting to explore leveraging faster sampling methods. Finally, our model is constrained in the maximum grid resolution by training time memory limitations. So this is what I thought, which is the quality of the model of the output and resolution of the output is really bad, and that's because the voxel grid is very memory consuming approach to encode 3D objects. Nerves are better when it comes to memory, but you cannot do this fancy masking with the nerves, so that's why they do the voxel grids. And this could be addressed by exploring adaptive or sparse grid structures, as well as factorized neural fields representations, which is basically some nerves that are better. Cool. So they basically talk about how this could be faster and that it's just doing diffusion, but on some particular 3D datasets. Cool. Yeah, so they introduced novel approach for 3D radiance field synthesis based on the noising diffusion probabilistic models. Cool. To the best of our knowledge, this is the first generative diffusion-based method to operate directly on volumetric radiance fields. Good for you guys, because probably someone's gonna publish the same thing in 2 days from you, so very cool. Our model learns multi-view consistent priors from collections of post images, enabling free view image synthesis and accurate shape generation. We evaluate DiffRF on several object classes, comparing it to performance against state-of-the-art GANs, and demonstrated that it works better than GANs. Awesome. Yeah, so that's it, I think. Cool. So let's look into the appendix, whatever there is. Yeah, and we'll be closing soon. Okay. Implementation details. Let's look at this unit architecture that they use for 3D. That might be interesting. Okay. We base our architecture on 2D unit structure. Okay. For this, we replace 2D convolution in the ResNet and attention blocks with corresponding 3D convolutions, preserving kernel size and strides. Okay. Furthermore, we use 3D average pooling layers instead of 2D in and downsampling steps. Makes sense. Our unit consists of 4 scaling blocks with 2 resonant blocks per scale, where we linearly increase the initial feature channel dimension of 64 to 156. We use skip attention blocks at the scaling factors of 2 and 4, and 8 with 32 channels per head. Okay, cool. It's nice that they give us exact recipe to write this particular model architecture. That's very nice. The training, Adam optimizer, from 4 random training views at a resolution 100 to 88 by 128, we sample 8,192 random pixels for the rendering supervision. What is 128 times 128 times 4. Like 65,000 pixels. So they actually not even train on the full image. They just randomly pick some subset of pixels, which is basically very interesting. So instead of training on the full image, because that would cost too much, they just pick basically 1 in an 8 pixels to calculate the loss. Okay, that's unexpected. Cool, interesting that it helps them, because that means that that means that basically different artifacts. I mean, it makes sense because we have multiple steps in the diffusion, and we do this image approximation in different steps. But it's interesting that they do this volumetric rendering only on 1 in 8 of the image data that they actually sample to train. At a voxel grid resolution of 32 on 2 GPUs on every dataset. We train for 3.3 million iterations with decaying learning rate, okay? On 2 GPUs on every dataset. They don't say how long. That sucks. Oh, they say what sampling is at least. So to sample for 1000 iterations, we have 48 seconds per sample. So this is probably per particular viewing direction, and you get 128 by 188 image. So very small thumbnail-like. Okay, data. So they discuss exactly how they render the picture. So obviously you don't want to render from the bottom of the object. So they discuss how they exactly set this rendering. They discuss how they calculate metrics, not very that interesting. Conditional sampling. Okay, so they talk about how they adapt this EG3D for this masking. Not very interesting. Okay, let's see what this image to volume synthesis. Given a post and segmented image, we condition our Radiance field diffusion model by steering the sampling process similar to the classifier guidance from DDPM. During sampling time for each time step t, we gradually update the predicted denoised field towards minimizing the photometric error obtained from comparing the rendering from a given pose with the foreground mask target image. Okay. So this is the approximated denoised field, and we do this trick where we move toward minimizing the error from rendering E of t from a given pose with the mask target image E. So this is our image that we use some kind of background removal on, and we remove the background, and we have this we have the particular visual error at every step of t, and we compute the gradient, and we update our denoising with this gradient standard classifier guidance. Yeah, so this is update with the gradient, and this is some kind of Gaussian's weight. The bigger this is, the less diversity you get, and the more the higher fidelity it is, but it should be still relatively small so that you don't break your latent. But this basically pushes your encoding closer such that the difference is smaller here. So basically the rendered image is closer to the actual image, and this way you can get output that is visually similar to your input image that you use for generation. So this is the clip conditioning that they mentioned before, which was very exciting. So they do the crest attention, and they do not train the image encoder in order to preserve the image text correspondence of clip. Okay, we show examples on single image, blah blah blah. in figure 14. So this is these examples that we just saw. Okay. As these codes have strong correspondence to the text samples by design, we can guide the sampling process by text prompts. Examples are shown in 12 without the need of training text radiance field pairs. Yeah, so they use clip now because clip allows you to encode text and images in the same space. So they can just input the attention from clip in a standard way, the same way you do with the 2D diffusion when you do 2D text to image diffusion, and they can condition with that the generation. But obviously they have two training classes, so they have tables and chairs, so they can only generate tables and chairs. So that's how it looks like. They can specify some additional information about the chairs, but I think it's starting to break. I think it is worse than what they do in unconditional case, or if they condition on the image. I think is much better quality here than here, because the clip is naturally noisy, right? So yeah, it's not a perfect one-to-one correspondence to some particular image, so it's adding some noise, and the outputs are naturally more. Okay, I think that's it then. Yeah, cool. So let me just quickly do a summary of this paper, and that will be it. Okay, so this DiffRF paper introduced the method for denoising 3D radiance fields. Specifically, they use voxel fields representation instead of NeRF or something like that. And it's very typical diffusion model you would expect. They train using two toy data sets of chairs and tables. And first they generate some NeRF representation, and they also some voxel voxel radiance fields representation, and then they also keep particular poised images for training. And what they do, they train typical NeRF. They use 3D unit architecture, and they train typical diffusion model. One thing that they specifically added to improve the results, they additionally have this volumetric rendering loss that is based on the comparison of specific post image with the rendering of the 3D voxel field. And this way they can remove a lot of assets, a lot of artifacts from the 3D voxel field representation. And they also introduced this interesting idea where this loss is much more relevant in the later stage of the this additional loss is much more relevant in the later stage of diffusion, because when we do the diffusion at the first steps, there is only noise. So comparing that noise to the image is not that important. But when we are closer, we can fine tune the results so that it perfectly matches the images of the ground truth data taken from different post directions. Other than that, this is fairly predictable architecture and predictable solution. I think the cool thing that they introduced is this masking idea, and that's why they decided to use voxel grid, I think, instead of using, for example, NeRF as the underlying representation. And they using this masking, they can basically denoise only a part of the 3D scene and keep the not unmasked part of the object as in the ground truth data, so they can reconstruct the rest of the object in any different way. Probably they could even in this particular mask part, they could also use some kind of clip text encoding to even say what this mask part should be like, to add some additional control. They didn't test that particular workflow, but I think it's possible with what they implemented. Unfortunately, it's fairly early paper, so they only compared to GAN-based method, and they treat all other diffusion models for 3D as concurrent work, other than older ones like Diffusion, which obviously we know was very cool, but not even close in quality to these solutions. And the results are good, but the biggest issue is that it's very small resolution, and yeah, and the quality of the output is not good enough yet. But I think it's a good direction of applying diffusion to this kind of 3D task. So I like it in general because it's clearly what needed to be presented, it needed to be tested, how this diffusion could be applied like that. And I think it's a good work. It's definitely not game breaking because you still need 3D data to train this for particular classes. So it's not gonna be zero shot, and we don't have the same scale of 3D data like for images, so it's not easy to make a stable 3D diffusion from this paper. But it's interesting direction, and I like it a lot. Yeah, so I think that's it. Thank you so much for listening and surviving with me for nearly 2 hours. It was cool going through this. It's a bit tiring, but I think very cool experience, and I will definitely do that more. So if you like it, you can like it, subscribe. Yeah, we'll be introducing more interesting research to this channel. So yeah, see you later, guys.